diplomacy actions. We now have a budget that has increased from £3.9 billion in the last 4 years, money spent already, committed and spent, and it's now been increased to £5.9 billion for the next 5 years. It's an extraordinarily well-resourced operation. And that money, the £5.9 billion, which sits in our international climate fund, is really to assist countries, especially least developed countries, to make the transition to a low-carbon economy and also create resilience. And that word resilience is absolutely central to what I want to say. You cannot adapt to climate change without climate services. It's absolutely essential because each region of every country is going to be faced with different challenges from climate change, and you can't guess that. You need climate services, you need big data, big computers to develop that capability for each region of the world. And that isn't a simple task. We can manage to do this on a 15 by 15 or 20 by 20 or 50 by 50 kilometer scale, but when you look at a small region of, for example, Rwanda in Central Africa, you need to focus right down on a small pixel scale. Tremendous amount of computer time required to do that. So that's just by way of introduction. Let's see if my slides come up here. Yes. So the first thing I'm going to do is take you back to when I was Chief Scientific Advisor working with Blair, 2003, working with Michael Evans as well as my private secretary. And in 2003, we had in Central Europe the hottest summer on record, and also, as a result, the biggest catastrophe in Central Europe driven by natural events. And this I say because I'm measuring it by the number of fatalities. The excess fatalities measured is about 50,000 due to that hot summer. So we've got a tremendously important event. It wasn't recorded in our newspapers as a cataclysmic event because unlike a volcanic eruption or a tsunami, this happened over a 4-week period. It was a slow burn, and the media not too good at reporting slow burns. I'm not going to be critical of the media, but so basically what you see here in black is the average Central European summer temperature going back to the year 1900. And of course what you see there is bouncing around is the annual weather changes. Now this curve I hope serves several purposes. What you also see in red is me going to the people who've got these large computers capability with greenhouse gases built into them and just saying, first of all, could you run your models backwards in time to see how well you can describe the previous summer temperatures in Europe to 1900 and then forwards in time to predict what will happen. And you'll see this is on a medium to high emissions scenario, which is the scenario we're currently on. They reinitialized the program. This is actually the Met Office. They reinitialized their computer program 3 weeks apart. And so what this does is by running several different reinitialized programs, you can see the weather looks like noise and the trend is what we're talking about, climate change. Right, so if we now go forward from 2003, there's that very hot summer, 1947, the previous hottest summer, considerably higher. And then if we roll forward in time, you get to mid-century, and you'll see that that becomes the average Central European hot summer in mid-century. That, to me, summarizes climate change and why we should be so concerned about it. Because, of course, in 2050, when we have an unusually hot summer, it's going to be a record hot summer for Central Europe, and that is what climate change does together with the weather. So weather gives us extremes, hot and cold, and the climate change is simply telling us how that average is spelling out. I don't have a more recent slide, but I'm not here anyway. But if you look at the way it has gone since 2003 to 2015, this is a pretty good description of that weather change and the climate change, not the weather change. So there's an example where we can look at this and say, well, how do we manage this situation? And going to the Prime Minister at that time, I said, well, there's got to be two responses. One is that's not a good pathway to be on, and that's a global response. Therefore, we have to reduce emissions. But the second is we're already challenging our ability to respond to these situations, and we will need to adapt. And so coming back to adaptation and resilience, climate service is absolutely essential. So as we go around the world, what you now have is 197 countries, all in need of climate services of the kind I'm now describing. That's an enormous task. How many operations around the world are capable of delivering that at high accuracy? Not many, certainly not enough. We actually need a learning process in which the capabilities of the European Centre at Reading and the Met Office and NOAA and so on are spread out into different countries around the world. That becomes absolutely essential. Of course, there are Met Offices in most countries, but having the ability to understand these computer programs is another question. Now, acting as Foreign Secretary's Special Representative, I've done two things, and I'm going to talk about them, and they both depend on handling large data. The first is this report that has now appeared. It's available on websites, which is taking a risk assessment approach to climate change challenges. Now, what this risk assessment approach does that is different from anything in the Intergovernmental Panel on Climate Change is it takes an insurance/reinsurance industry approach. I suspect anyone who owns a house here has got an insurance policy against fire. Not because you think your house is going to burn, because you think there's a chance it might burn. So what a risk assessment does is analyze not what is the most likely thing to happen, which the IPCC tends to do, but what is the most extreme thing that climate change could throw at you, and then we can look at percentage chances. Now, let me just tell you that when I was Chief Scientific Advisor, this was a big part of my job. Right? So I had to worry about things that had a low percentage chance of happening, but where the outcome for the British people was massive. And I'll give you a very simple example, H5N1, avian flu. That was an avian virus, which meant we could not contact it and then transmit it to other human beings, but it had a chance of transmuting into a human-to-human H5N1 virus. Human beings around the world have no protection against H5N1, and we therefore knew that the consequence of this happening would be dramatic. So what I did was get biologists to give me an estimate of the transmutation probability, and over 10 years they said roughly 1%, no more. And then the epidemiologists to say, if this happens, and here's the large data computer calculation, if this happens somewhere randomly in the world, how long before it arrives in the UK, and what would be the consequence 6 months later? Well, it turns out within 3 months, it would be everywhere in the world, basically because of airline travel, a very good way of taking virus in human beings around the planet. And within 6 months of that time, the estimate was something like 500,000 to 1 million deaths in the United Kingdom. And the outcome of that sort of number was then examined, and we realized our economy would collapse, and at the same time we'd have global economy collapsing. So we then spent quite a lot of money. I won't even tell you how much, but it had many zeros in it, because I couldn't go to the Prime Minister telling him this without having a solution. And the solution then was GlaxoSmithKline develop a vaccine against the avian H5N1 and inoculate the human population. Anyone who's had a flu jab has had this in their flu jab, so most of us have had it. and we are inoculated against H5N1, yes, you'll have serious flu if it becomes a human virus, but you're unlikely to die. Right? So that was the equation we used, and we did it. That's the approach we're now using in this risk assessment analysis. So we first of all brought together about 120 experts, and the experts were not just science experts, reinsurance and statistical experts, but also political advisors, diplomats, scientists, and politicians from China, India, the United States, and the UK. And we met in each country. Now, the first thing I asked them was, given political appetite for change, what is the most likely outcome from the meeting in Paris? And they said, yeah, it's likely that an agreement will be reached, but it's likely that it'll still be a 3.5 to 7 degrees centigrade world. And I'll take you through that. We then used that pathway and asking each country, what is the worst that climate change may throw at you? And then we analysed the outcome of that. I'm just going to show you a taster, but please, there's one copy I've brought along here, and it's all on the website. Please do look at it. This, I think, is the most important document for the political system to read. Those people who were involved in the program, including myself, were rather frightened by the outcome. Right, so here you see the first question. This was asked by the Chinese, but we applied it to northern India and southeast US as well. And the question was, that number of fatalities in Central Europe in 2003, when does that multiply to several 100,000 people dying? And the estimate from the human biologists was, if the temperature is above 4 degrees centigrade, is 40 degrees centigrade for more than 3 days, and people had no access to air conditioning, fatalities would rise to those levels in these parts of the country with this percentage chance in a given year. So we got the probabilities going from 0 to 100, and you'll see that there's a rather surprising sudden increase when the global temperature rise is 4 degrees centigrade plus 0.5 to 1 degree centigrade. So it becomes a very likely event in any given year in these parts of the world. Now, that's obviously cataclysmic in terms of the fatalities and the impact that would have on their economies, but also the global economy. But don't forget, at the same time, climate change is throwing a whole series of challenges around the world. So the next challenge was, okay, what's the probability in China of our rice crop failing? And they're talking about the 3 major rice crops that produce the major part of the food for China. And so we looked at that. This, in a way, is more frightening. If you look at just the local temperature increase, the top of the horizontal axis, you'll see that the cumulative probability starts going up as the temperature just begins to rise from where we are today. Now, that's the local temperature increase. The probability of losing 1/3 of the rice crop becomes quite high. And if you look at all of the rice crops there, you'll see that even the green one is rising into that 1% level. Now, this is just the impact of temperature rise. At about 35 degrees centigrade, as the rice plant is growing and flowering, if the temperature reaches 35 degrees centigrade, it doesn't produce the fruit. Right? So this is based on straightforward biology. Of course, genetic modification or breeding of plants that have higher temperature resistance during flowering is something that points to as an outcome that needs to be explored. But then we also look at rice production globally. The biggest rice paddy fields in the world, the biggest rice producing area, is the Mekong Delta in Vietnam. Mekong Delta, that's basically at sea level. You've got a river flowing down, rice paddy fields each side of the river, sea levels rising, you can see what's going to happen. The salination of those rice paddy fields due to storms at sea will happen before the sea level has even reached the paddy fields. And then you've killed off the opportunity for growing rice there. So one of the things we did in the final chapter was look at systemic outcomes of all of these climate change-driven events. So what is the probability of exceeding 4 degrees centigrade? That was the critical point where we see the number of fatalities suddenly taking off in a given year. And you'll see that on the business as usual scenario, the red scenario, which is very close to where we are now, we get to above 1%, which I'm saying is what to be avoided just after 2050. And as we move into the next century, that's got a 100% chance of happening every year. So you're looking at that danger zone where human beings in many parts of the world will not be able to survive going forward in time. I've been criticized before for not talking about raising air conditioning around the planet, but all of you know that's an energy-intensive process. That's going to cause a feedback that is not in the desirable way unless the energy is all solar energy produced. The likelihood of driving in this relatively short period of time air conditioning into every home in the world is pretty small. So let's not rely on outcomes that are very, very unlikely going forward in time. But even, I think, alarmingly, if we look at these are the IPCC scenarios, IPCC, the only scenario that really works is the blue one, the dark blue one, and the current contributions nationally that have been put forward for the Paris meeting are more like between the yellow and the red one. So we're not even close to that dark blue one. My constant harassment of the global political system is we've got to go for that dark blue one. That's the one we need to be on if we want to actually make sure that, just to give this a very personal tone, my granddaughter actually can have grandchildren. She's 1 year old and she'll be around at the end of the century. Now, you could say the probability of exceeding 7 degrees centigrade, IPCC never refers to that probability. And yet, look at the probability. This is IPCC data. This isn't new science. We're using their data. The probability of exceeding 7 degrees centigrade beyond the end of this century goes very, very high on the business as usual scenario. That, for me, is just the outlier that ought to be up there. It becomes more than likely to happen in a given year than not happen, that the temperature rise would be more than 7 degrees centigrade. Now, of course, the global economy would have collapsed before then, and you would say, well, therefore carbon dioxide emissions will have collapsed as well, and that's right, but it's not a very good alternative outcome. Now, for Britain, and for any island nation, this is probably the most frightening curve that I'm showing. So this is long-term commitment to sea level rise. Largely, the sea level rise that's been taking place has been due to the warming of the ocean, but more recently, other contributions stepping in. And as we move forward in time, the biggest contribution is from land-based ice melting and going into the ocean. And as I'm sure most of you know, if the Greenland ice sheet melts, sea levels rise by 6.5 to 7 meters globally. Now, what the scientists are showing is that today the Greenland ice appears to be melting on a potentially irreversible pathway. Right? So the ice on top of Greenland reflects sunlight very efficiently back into space. But when the ice melts and forms a lake, the lake absorbs the radiation much more efficiently, and so we begin to see the speeding up of the melting process due to the higher absorbance of the radiation. And so this is the best analysis available, the temperature rise. That is from the present time, not from pre-industrial time. And you'll see that with a 1.5 degree centigrade temperature rise, we're already in the middle of the probability curve. And this is the probability analysis where the sea level rise goes up to 10 meters. And so that of course, would change the shape of Britain, literally, very dramatically, we would get considerably smaller. But 80% of the world's cities would be underwater as that begins to happen. Now, the scientists are not very good at telling you what is the time scale. This is just temperature rise against sea level, but the time isn't there. And if I tell you the estimate of the time is somewhere between 200 years and 2,000 years, you can see that there's quite a big piece of work still to be done on what the time scale of that sea level rise process will be. Of course, part of the problem is that the melting takes time after the temperature's got to the point where it's become irreversible. So it all becomes a bit late to deal with this when it's already past that irreversible point marked by that relatively vertical line here. I need somebody to indicate when I've got a few minutes to go. How much time have I got? 2 minutes, okay. Let me then very quickly say the other part of my work is how do we get ourselves onto that dark blue curve that I mentioned. Well, the required path that I produced back in 2013 is shown here. The forecast from the International Energy Agency, billions of tons of carbon dioxide equivalent emitted per annum as a function of time, 1990 to 2035. But we're still on the red curve, so we've got to come down more sharply than represented by this curve. The estimate at the moment from the intended nationally determined contributions, which are about 157 countries today, out of 197 have submitted them, corresponding to 93% of emissions. The estimate is something like 12% down from that red forecast curve, and the commitments actually don't go beyond 2030. So we've got a very, very long way to go to get down onto that green path. That's a complicated curve when you're told you've got 2 minutes. Let me just quickly move on. What is needed is the rollout of a combination of renewable energy, energy storage, and smart grids until that combination is cheaper everywhere in the world than fossil fuel-based energy production. And I'm saying energy, I mean electricity and heat. We've got to tackle both. Now, first thing is this slide is saying actually the situation is more optimistic than I've been making out, because there's a technological revolution happening under our feet. In 2014, more renewable energy installed around the world than other forms of energy. That's primary energy. In Britain, we've already got nearly 12,000 companies in the new low-carbon economy. That was just about zero 15 years ago. Now, this is the fastest growth sector in our economy today, not reported in our press. Critical piece of information. Nearly 500,000 people employed in this sector. Why isn't that out there? If this was out there, wouldn't we see many more statements from principal figures in government boasting about what has already been achieved in the UK? This new growth sector. Annual turnover in 2013, £44 billion, but the growth rate over 3 years, 30% growth in this absolutely new sector in our economy. What this has done through feed-in tariffs is to pull down the cost of photovoltaic installation and the cost of wind turbine installation. Technology rolling out different solutions, competitive solutions, different companies coming in to the marketplace, and we're seeing a massive transformation. So the cost of installation 2014 is down at 0.4 pence per watt from up there, more than $10 a watt when feed-in tariffs were first introduced, and still going down. We're down at $0.3 a watt today. What that means is that already installation of primary energy is competitive with coal anywhere in the world, but it's intermittent. And intermittency is the big problem today. And what we therefore need is a focus of publicly funded research, development and demonstration. I believe particularly into the areas here: storage, transmission, development of smart grids, grids which use electricity when it's available for a whole variety of things, and stop using it when electricity is in low supply. We need to see that we have smart grid transmission, storage and renewables. That combination is what is really going to make a difference. We're calling for an overall program of at least $15 billion a year of publicly funded research, development, demonstration, with the private sector coming in the slipstream. The public money de-risking these new technologies into the marketplace and the private sector following through. This is something that a group of us launched as the Apollo program back in June. I believe that we're going to find several heads of government supporting this when we get to the COP in Paris. Thank you.
Thank you very much, Sir David. I think you framed very well the questions that we have in front of us, which is two-sided. Actually, it's time for action because our Earth climate is changing. And the other one is that this information actually creates already today an opportunity for growth. And that's exactly what I will be talking about with the Copernicus program. So the European Union is not only driving efforts at the global scale to get a global deal with ambitious carbon reduction commitments, but it has also funded in its budget for the period until 2020 this program called Copernicus. And Copernicus actually was born just after Kyoto in 98, the idea of it. The idea was that the observing capabilities that we had on our environment, the slides that Sir David showed actually, they are very rare because observations, reliable observations of the different compartments of our environment were relying on very thin pieces of observations. So what brings the European Union with Copernicus is an operational capability to monitor the environment with those two objectives. One is to document how our health system is changing, and the other one is to develop the European economy and provide opportunities. So this is done by means of developing the observation infrastructure. The largest fraction of the budget of Copernicus, which is about 4.3 billion euros, is launching satellites with a dedicated capability to monitor our environment. These satellites are called the Sentinels. And as such, a Copernicus tagline, which is Europe's eyes on Earth, is becoming a reality. 2 of these Sentinels have been launched already, and the program stretches until the next decades. So how Copernicus is organized in a nutshell, this is about acquiring observations from the Sentinels, which are funded by the program, but also from lots of other sources of observations. Other satellites worldwide from our North American colleagues, Japanese colleagues, etc., but also very importantly on ground-based and in-situ observation means. So it's about acquiring all these sources of data and then transforming these raw observations, combining them to develop information services. So the Copernicus program is shaped into 6 different topical areas or services, which deliver each products that are relative to those themes. So the European Weather Center is managing, operating 2 of these services. One is concentrating on atmospheric composition, so we'll show you some example, and the other one is working on climate change and climate services development. And all these services and products, they are made available freely, openly, transparently to all users, policymakers, in order to base policy development or policy monitoring on facts, on evidence, the general public that may be interested, that is often interested in questions like air quality, as it links with health, etc. And of course, the private and commercial sectors that can use this huge source of open data to develop business and innovation. The way it works in a nutshell is crunching all this data worldwide. So from satellite, I mentioned that, but that's far from the only source of data. Monitoring from the ocean, buoys or ships, monitoring from the ground, or monitoring also remote sensing from the ground. All this information is compiled and gathered together using actually the same infrastructure that is used on a daily basis for weather forecasting. This is compiled using supercomputers, using also the best academic expertise throughout Europe and archives so that applications can then be developed in terms of future scenario. Where are we going in the next few decades up until the end of the century? In terms of short-term to seasonal scale forecasting, so from a few days to a season ahead. Climate monitoring, so how this climate is evolving year after year. So I will show you an example which is similar to the curve that Sir David showed with the temperature. And also atmospheric composition monitoring, so that's how the greenhouse gases, how the particles in the atmosphere are evolving. And this serves a wide range of users. This is clearly big data. Just to give you a number, one of the products of the climate change service is a reanalysis, a compilation of observations and models covering the last 40 years. This data set alone has a volume, will have a volume of, we are starting to produce it, will have a volume of 6 petabytes. And 6 petabytes is actually 6 million of billion bytes. It's enormous. So if it was stored on CD, the pile of CD, without the cover actually, the pile of CD, each one is 1.2 millimeter thick, would go up to the highest clouds, 11 kilometers. If we printed that data on books, there would be enough to reach up to the moon. So we are really in the area of big data, and this is only one of the data sets that Copernicus is producing and making available to wide audiences. One area where Copernicus is very active, and already today, is to monitor how emissions drive change in the composition of the Earth system. So I have here this iconic time series, which are observation of carbon dioxide, which were taken since 1957 in Hawaii on the Mauna Loa. And you see this curve, which is oscillating on a yearly basis and growing up to 400 parts per billion, which was crossed a year ago or so. So this is the evolution of CO2. As you know, CO2 is a greenhouse gases, and from the basic laws of physics, we know that this will drive the Earth system to a hotter status. But CO2 is not the only compound that is able to modify the Earth system through modification in the radiation of the solar radiation. Also, there are other gases like methane, nitrogen peroxides, or particles in the atmosphere. So what does Copernicus offer today is to compile all this information, and one of the products that we've been delivering in particular to the IPCC, combining surface-based and satellite observation, is an assessment of how the fluxes in CO2 have evolved since 1979 on a monthly basis. What you see here is either the release, there are the colors in red, or the uptake of carbon dioxide from vegetation. You see clearly Amazonia, for instance, at the global scale. And we can see not only this curve going upwards, but we can actually look into the engine and see what are the emitted quantities of CO2 and what is the uptake of CO2. So we have a clear understanding of the relationship between the human activities, that all the combustions that emit some of these CO2, and the way the Earth system is responding by offsetting some of that naturally, but also by not compensating this completely. Another product which is very well in the front of our Copernicus offer is data sets spanning a century. So what is shown here is a reconstruction of the day-to-day variability of the weather and climate from 1900. What you see as bars with blue and red color is the evolution in time against the average for the whole period. You see clearly a warming trend, even if on a yearly basis you have oscillation, as was also shown very clearly on the graphics shown by Sir David. And what is depicted as maps are the average for the first decade, a decade in the middle, and the last decade, with still the same color coding of red being hotter and blue being colder. So it's very clear that something is going, that the Earth's climate is getting hotter. And actually this led some scientists to propose the term Anthropocene, that is the period where human activities are affecting the climate, and in analogy to geophysical epochs, such data set actually can help dig into the processes that have been ongoing since the start of the industrial period, and also very importantly serve the purpose of evaluating the models that we use for the projection. So the curve of Sir David was showing the past and the future. For the future, we have no observation by definition. So we rely on models. And a critical question is actually whether these models are accurate or not. Can we trust these models? And this data set is one of the key data sets worldwide that can be used to assess whether the models that are used for the projections are accurate. One of the challenges of Copernicus is not only to produce this big data using the best of science, the best of technology, but is the biggest challenge is actually to reach out to these users. So to reach out to the governments, to give the latest figures, to monitor how the emission reductions impact actually on the environment. But it is also to facilitate access to businesses or to the public, which means to open up the access to this big data using all the modern technology that is available. And one of our big tasks in Copernicus for the coming few years, 1 or 2 years, is to develop capabilities that will allow anyone, SME, a private person, to download the piece of data that he or she is interested in to develop applications. So in this, certainly, we are looking for innovators, we are looking for investors, and our job is actually to support them and so that they can access this data. I've taken one example of applications that could be fueled by the Copernicus program, and which is already fueled in some areas by the Copernicus program. It's about the energy sector. So I'm introducing this sector. The next speaker, Kevin Sara, will speak with more detail. But with Copernicus giving information on snow, ice, river runoff, so there is information about the hydropower capabilities. It's also giving information on winds, and so it gives information on the potential for solar energy. It also gives information on clouds, on aerosol particles that affect the solar radiation that comes to the ground. So that gives information of the solar potential. And overall, if you think of all these energy sources as part of a grid, due to their intermittency, the fact that we deliver an information which is very timely, very frequent in time, allows to target the infrastructure and target the grids that will stand in the coming decades. So the energy sector is one example. Other examples are water sector. Another example could be tourism, and Copernicus will support development in these sectors of the uptake of the raw data to make real-life applications that are profitable. My last slide is just to show you or to initiate your curiosity about other applications. Some are existing today. Some of the Copernicus data today can give you information on air quality. So there is one application, you know, maybe, which is called AirTex, which gives air quality in London at a very high resolution. This AirTex system, which is operated by CERC, SME, actually uses Copernicus data as boundary conditions. So whenever there is like a dust storm coming over the UK, this dust storm will have effect so that the information that is delivered through the AirTex system can take this into account. Another example of application we can think of is estimating how the flood risk may evolve in the future using the projections at a very coarse resolution and then using tools to downscale this to a resolution which is useful either for site planning or making a decision on a certain place. So that's all for my talk. I'm very glad now to introduce Kevin Sara, who will be digging with more detail into the solar energy.
So I really just want to go into a little bit more detail about the importance of the satellite information for the solar industry. I think that Sir David has really put it into the context of how important it is, this whole the climate change issue, and that we have to do something about it. And how do the practitioners, the people who are actually trying to make the changes and to introduce renewable energy on a very, very large scale, what are the main issues, and how can a system like Copernicus help us? And we're already using Copernicus, and our colleagues are as well. As you see, there's been an explosive growth in the last 10 years of solar energy, and it's really being deployed on a utility scale in very, very large power plants. It's become, in the US market, and I think globally, it is surpassing the installation of fossil fuel power plants. Now, when there were small projects on farmers' fields, if you got the numbers off a little, it didn't really matter that much. But when you're building 500 megawatts at a time, there's recently a tender for a single project of 500 megawatts in India. And if you get the numbers wrong, and they're very competitive tenders, the investors end up losing all their money. If someone recalculates, they realize the project actually can't be built at that cost, and it becomes very, very serious business. So having accurate data is extremely important. And there are different types of data which are important. It's not just the solar radiation, but there's also a whole series of other information which are very important. And the information really depends on which type of solar technologies that you're installing. The one which captures most of the press is PV, where it's relatively simple in terms of the data required. But another technology which our company specializes in is called CSP, where we use the direct sunlight. And there, intermittent clouds, temperature, wind have a big impact on the daily operation of the power plants. And it's very important that we have this information and that it's available and that it's accurate, because this technology can actually solve the intermittency problem. And you can integrate storage very cheaply, much more cheaply than with electric batteries, which is why we need to invest so much in R&D to make batteries cheaper. But until then, this solution works. This just gives an example of the production curve that you can achieve with a CSP power plant compared to the production curve of a PV power plant. And what's interesting is that in many economies, the peak tends to be in the evening, when the PV plants start fluctuating very strongly or just declining very rapidly. And with CSP and storage, you basically save the heat and you continue to generate electricity right through the evening hours and even into the night. Now, the key variables we need for PV is obviously the total solar resource and the temperature. The temperature has a big impact on the output. Wind data is not that important. On the other hand, a windstorm can shut down one of these power plants. So it's extremely important to have good wind data, and also this whole aerosols and dust in the air really can have a big impact on the output of these plants, because you're bouncing around sunlight and concentrating it, and if you have a lot of dust in the air and in the solar field, it can really have an impact on the output of the power plant. We've already seen in practice the lack of good satellite data and the level of accuracy of projections has an impact, is an issue in the industry. For example, in California, one of the largest CSP power plants has underperformed because the solar radiation simply has not been what was originally anticipated. And some analysts attribute that to changes in the weather patterns due to climate change. But it's still an issue, and it's an issue in the siting of the plants. And again, a plant actually had to be relocated from its originally anticipated site, because when they did more accurate ground measurements, the data was way off what the satellite data was telling them. So there's a real need to have more accurate satellite data, and we'll make a few points about how we think that can be done. And then also, if you do not have an accurate forecast of the wind environment, it can have a big impact on your output of a CSP plant. And in this particular case, in Abu Dhabi, they've needed to actually build physical wind barriers. One of the issues that concerns the industry is that a lot of the power plants, and even in PV plants, when you start going up to the hundreds of megawatt scale and the gigawatt scale, you want them to be built in very arid areas, or areas which are almost, in the case of CSP, are quasi-deserts. But they can't be too far away because you need to build the transmission. So they're kind of like these boundary areas, and we're quite concerned that these boundary areas may be the ones most affected by climate change and changes, macro changes in weather patterns. And so this is something we're very interested in working with Copernicus and climate scientists to really understand the impact of climate change on the long-term weather patterns, and because this will affect our decisions on where to site solar power plants. What our dream from for big data, I asked my technical team, like, we have the opportunity to give a message to Copernicus, and what's really lacking. One of our issues is the ground stations and the location of ground stations. And usually where you want to build the solar power plant, there is not a nearby ground station, so you do not have the ground data to correlate your satellite data, so you can make your time series. And what the industry has had to do is set up our own mini weather stations, and we literally haul them out to sites and set them up and take our own solar data measurements, wind measurements, temperature measurements. And the problem is, to have a bankable project, you need to have several years of data. So this really slows us down. And if we had more accurate satellite data which was properly calibrated with ground stations which weren't too far away from where the main solar development was occurring, it could really speed things up. I mean, right now, if we found a good site and there's the other conditions, there's a buyer for the electricity, it will still take us several years of development. And this is for a CSP plant because you need much more accurate weather data. It will still take several years just from the delay of having to collect the solar data. Finally, we've been developing a power plant on the island of Crete. And for most of the year, it's beautiful blue skies, but then there's about a third of the year where you have clouds which appear in the sky, and we have to really be careful about forecasting them and understanding when they're coming, because we have to give a day-ahead forecast to the buyer of the electricity. And so if we don't have a good sense of what the weather is going to be, we can be financially penalized. So we've developed a system where we set up cameras which look at the sky ourselves. We shouldn't be having to do this. This is not our core business. So this is something that we'd like to see the satellite data providers do for us, and that would really allow us to focus on our core business. So just from the perspective of the solar industry, having access to this kind of data can really help accelerate deployment of solar on a very large scale. I mean, what's helping solar right now is just the prices have come down to the point where it's beginning to become competitive with fossil fuels. But what's really going to help us, and what is really going to allow us the industry to accelerate on a really massive scale, is having really accurate data, getting the confidence of the investors that that there's still a lot of a doubt in investors' minds on the future performance of the plant. So if we can have more of a partnership and work more closely with the providers of big data, I think it would do a lot to help the industry. And I had some very nice slides at the beginning which showed the explosive growth of solar, and how we're actually putting in, I think if you include wind, it's more than fossil fuel on an annual basis globally. It still accounts for, I think it's less than 1% of global generation. And if we're going to do anything about keeping on the curves and keeping the planet safe, we need to do, the solar industry has to be scaled up far more than it is today. And that will entail really building out massively both PV and CSP. And again, CSP does resolve the intermittency issue. And of course I have to, since I have a captive audience, I have to give a little advertisement for our company. One of our main projects, we have a very nice project in Greece, but we're also developing a very large-scale solar energy CSP project in the Sahara Desert in Tunisia. And this project includes an interconnector which will connect the output of the power plant to the European grid. And this is something that we're able to export power, renewable power, which has got storage integrated, so it's base load renewable, and we can export this power at a very competitive price to continental Europe and even to the UK. And we can do it with very little subsidy, probably less subsidy than any other renewable, because of the storage we deliver into peak times, into the most expensive times. So I'd just like to leave that thought with you, and this is something that can be really scaled up, and this is something that we're looking forward to working more closely with Copernicus to do. Thank you very much.
Thank you very much, Kevin, for this very interesting talk. So we have time for some questions from the panelists?
Hi there, Mark Partington from Ost Energy. I'd like to ask Sir David, who talked about the importance of the cost, of renewables versus traditional fossil fuels. And I'd like to ask how important carbon markets play, and whether in your thinking you're including is it unabated, or are you including a carbon price? And we've had problems in the EU ETS with the markets being oversupplied not once but twice. On the positive side, China's announced plans for a federal carbon market, and I'd also like your thoughts on that. Thank you.
So very, very quickly, I think the positive feature with carbon prices is emerging as more and more countries start developing them and begin to merge their carbon pricing with each other. California, working with Quebec, is the first such example, even from state to state across different countries. But we're a long way from reaching carbon pricing covering all countries in the world. And yet, in the next few decades, we have to roll out the sort of energy that we've just been hearing about from Kevin Sara into developing countries so that they leapfrog into this future. So, no, I'm not counting carbon prices in. And what this means is that for energy storage, we need to be talking about $100 per kilowatt hour or less, the cost of installing energy storage. So any development needs to be always looking at costs. Energy storage with lithium-ion cells is never going to reach that price. I know that there's a big American company in California rebadging Samsung's cells in a very beautiful way. It'll never reach that sort of price. So we need some wonderful new ideas, and there are some emerging. We've got to hit the global market without a carbon price. Now, it's not all bad news. There's some wonderful news there. 623 million Africans have no access to electricity. They're all in small off-grid villages. The British government has now decided that within the next 15 years, we're going to roll out electricity to all of those villages using solar energy with batteries and microgrids. So even using the lithium-ion cell batteries as they cost today, that's 3 to 4 times cheaper than extending the grid to those villages. But I think what is attractive about this British scheme is that it creates another huge market. And it is a market. We're using our $18 billion a year aid to develop the program, but it's going to be a market. And so what we need is more markets to pull the price down.
Hello, Tim Price from the Carbon Trust. Just a question about the Copernicus data, and just help me understand a little bit better what it can do and what it is. One of the things we're trying to do at the minute is to look at the potential effect of climate change at the city scale around the world. And I had the question in my head, would it be appropriate to use particularly the forward-looking, the kind of forward modelling and forecasting element of this data at the city scale? And what I think I'm asking, is it all out of a global climate model, or are there downscaled regional climate modelling efforts in there that we could use at the city scale?
Yes, the Copernicus program is primarily global and also has a focus on Europe with higher resolution, but we are not reaching out really to the urban scale. It's more the way Copernicus has been set up is basically to bring to scientist operators that can do the last step, which is the urban modeling of the emissions, interaction with the urban thermodynamics, etc., to their fingertip, because they couldn't do that in isolation. They need all the context, all the radiation that comes in. And what Copernicus brings is this context to, so these urban scale applications are so-called downstream to Copernicus. Copernicus is bringing all what's needed to build in a statistical model or a deterministic model that will go down to the local area. Copernicus is a European program, so we have a mandate to cover the whole of Europe. We couldn't afford, of course, to cover each and every city in Europe, let alone in the world. So the way the program has been set up is to bring to a scale of about 20 to 30 kilometer horizontal resolution at the global scale for our main products, and then something around 10 kilometer over Europe. So we are far from the urban scale, but still delivering data as an input for that.
Thank you very much. Sara from Water UK. You mentioned flood forecasting. Are there any other applications you can think of for water providers, for example, drought forecasting as well? And will the data that Copernicus provides help us better explain the narrative, the connection between water, food and energy for all our customers?
Yes, well, Copernicus is bringing facts to the table. So we have, as part of the Copernicus program, the flood forecasting element, which is covering Europe, which has been very useful in very recent cases. The question is how to use this data and transform that into information. Copernicus, as we operated at the European Weather Center with our providers, will not go all the way to all the interpretation. We are, I would say, delivering basic information. So you have the flood, you have the information coming from the projections with the runoff, with the snow, with the rain. And this is delivered to users. But the Copernicus will address some of these questions, but certainly not all of them, leaving room also for businesses. And that's part of Copernicus has two aims. One is to monitor the environment operationally. The other aim is to grow businesses and jobs in Europe. The target for Copernicus is just about 50,000 jobs to be created until 2020. So this is very challenging, and it means that we should refrain from going all the way in some places because there is business, because there are customers that are ready to pay for the extra mile, which is coming from the raw basic data set that we deliver to something which is really fitting their own tailored needs.
So Jane Dennett-Thorpe from the Department of Energy and Climate Change. Sort of building on the last two questions, and I think when the Sentinel series comes online, we're going to have an amazing wealth of data, and the Copernicus program is going to be extremely informative. And I understand from what you've been saying that your focus is really on providing that data, turning it from raw satellite data, which is of no use to anyone, into something which is going to be useful to wide communities and making that accessible. But you're also saying that you're going to be developing some services, as in turning that into information which is usable by people answering specific questions. I wondered if you could try and say a bit more about how you're going to determine really when you're just providing the data, which is itself a useful service, and when you're actually going to be focusing on trying to answer questions that people want to know.
Yeah, at the core of Copernicus, there is a committee and a user forum which is driving fully the program. So this Copernicus user forum, which is composed of representatives of all the European countries, actually is the place where these questions are answered. That is, what is the limit between what Copernicus as a public good, public service is delivering, and what are the areas where Copernicus should go because there is no market, or because for some reason all this Copernicus committee will agree that Copernicus should really reach out to the public. So in some areas, Copernicus is reaching out on air quality. We are delivering European scale air quality maps already today because it was seen that with a large episode of air quality, the European dimension is very important. We've seen very recently lots of examples where air pollution in London, for instance, was connected to air pollution in the Benelux, in the north of France, was connected also to sarin dust. So clearly, this made sense that the Copernicus program would deliver maps and forecasts of air quality at the scale of Europe. Now, if we are speaking London, it would be very damaging if Copernicus was delivering a very high resolution forecast, because there is a market, because there are operators that can do that. What we bring to them is the large-scale information, but then the last mile, it's up for them. So this Copernicus is a user-driven program, and this is very real in the sense that on a yearly basis, how Copernicus evolves is discussed in Brussels. These committees meet 4 times a year. There are national events. Maybe some of you have been invited to events in the UK, where potential users, Copernicus representative in the UK discusses these elements to drive the program in a sense that maximizes the impact of Copernicus.
Hi everyone, I'm standing up so you can actually see me. My name is Benjamin Kott. I'm founder and CEO of a startup that's actually sitting here at Ideal, so one of the Cisco-sponsored startups. And I used to work for Google during the Ivanpah acquisition or investment, as Kevin might remember back then. I have a question about the role of technology versus policy. I haven't heard too much talk about policy, which might be a good thing apart from feed-in tariffs and so on. But I was wondering, because I was at COP15 back in the day, and we were trying to make things work, and we were working with IPCC on visualizing their data from AR4 on Google Earth, which is quite fascinating if you see the time slider running over 100 years, and you can see the polar caps heating up to 12 degrees, even in the not most aggressive scenario. And now we're back at COP21, and we're trying to do it again and to go there again. What we really need is a minimum carbon price of $30 per ton, $40. We need binding targets and so on. I'm not sure we're going to get this out of COP21 even. And as you said, Sir David, we're running out of time. We might already have run out of time to an extent. At the same time, so I'm also an aerospace engineer and got a technology angle. We have the technology today to solve that, to solve 90-95% of problems we have. Renewable energy, other applications and so on. We're working on one of them for the built environment. So finally, the question to the panel, what do you think is the relative roles of policy versus technology? And if it's more technology driven than policy, and if you believe that business cases there, we just need to get them out, what is lacking today? Why isn't everybody already doing this? How can we connect the dots literally for people out there to make it all work? Thank you.
As more of a practitioner, I'm sure Sir David will give us more of a policy perspective, but policy has a huge impact. I don't think we'd be here today in renewable energy without the policy initiatives of the Green Party in Germany, who basically launched a global solar revolution. And then the subsequent industrial support of the German government and the whole rebuild of East Germany and the Solar Valley. I mean, it's quite extraordinary, and it was government intervention. And also, if you look at the actual invention of technologies in solar cells, and that was in a quasi-government lab in Bell Labs, and they've all had a lot to do in universities. A lot of the universities have a huge role to play. So there is this government policy which plays a primordial role in the development of the invention of new technologies, and then facilitating their deployment. I mean, at the same time, policy has got to be carefully calibrated to allow the private sector to really run with new development. So, you know, my answer to the question is like absolutely, you've got to have the right policies, both on the R&D side and also on the deployment side.
Yeah, big question, and I kind of evaded it in my presentation. So I think what I want to do is just divide your question up into 2 parts. One, international political gatherings such as the UNFCCC, and secondly, governments. And what Kevin's been referring to is particularly the German government, 1989, introducing feed-in tariffs and transforming the world in a big way. So just starting with the international scene, and I've got to be very careful with my words, The Paris process is critically important. So nothing I'm about to say should diminish that statement. However, 21 years to reach an agreement, this is practically a failed system. Yes, we got an agreement in Bali that we would limit temperature rise to less than 2 degrees centigrade, but we never created the practical process that would deliver that. Paris is the first step on because the Kyoto process failed in Copenhagen. And the Kyoto process was, as you know, top-down. All developed countries would have a carbon cap and trade. We would have a nice high carbon price. The technologies would flow through. I'm going to say I'm somewhat skeptical about a high carbon price driving the technologies through. We had oil prices at $150 a barrel, and I still saw a lot of cars driving around. So I don't think carbon prices would ever have changed from $45 a barrel to $150 a barrel. So but there are many, many people who believe that the market system is going to deliver, and I'm not going to say it won't deliver. It cannot deliver on its own. That's the position I take. We need regulatory levers as well. And what has produced the results, as Kevin says, was actually regulatory levers. But these were not developed through the international scheme. Even the carbon cap and trade in Europe was a European go-it-alone. Although we waited for Russia to sign up to the Kyoto Protocol before doing it, that wasn't really necessary. We went alone on that. Now take country by country what is happening, and it's tremendous. We're already seeing so many countries adopting regulatory levers that are producing the right sort of results. Let me say, starting with China. And one of the issues that I do want to say is climate change alone is not enough of a driver for many governments. So in China and India, the two critical countries in terms of the growth of their economies, it's C2.5 particulate matter in the cities. So it's urban environment that is absolutely critical. If any of you have been into Delhi or Beijing in the last year or two, you'll know what I'm talking about. It's back to the smogs of London in the 1950s and worse. It's 15 years is the average reduction of lifespan for people living in Beijing and Delhi today. Now that's a big driver for governments to shift away from fossil fuels as well. So the international political system is about to change its nature after Paris, but a big stress I want to put on this is the work starts after Paris. Paris isn't the result of all of this process. It's the beginning of a new step in the process. And by that I mean governments will, the biggest risk for me is the governments look at Paris and say, we've done it, and walk away from it. Actually, I'm continually saying to governments, you need to tell Europe to do better than 40% reduction by 2030, and I need to be telling you to do better than what you're currently promising. The work begins after Paris, but it is government legislation, government regulation, plus carbon pricing, all of the above is needed, because the renewable technologies are the new boys on the block, including Kevin here, against a mature industry. And the mature industry is very, very price competitive after 100 years of fossil fuel plus. And so we need to give a boost to the renewable sector until it is competitive.
Thank you, everybody. I think that's as much time as we actually have, and we're about to lose the room. So thank you to the panel, to Kevin, to David and Vincent-Henri, and thank you to you guys for coming.